It starts at 10? Oh my God. Will you guys be able to come in at 10 and then leave at 12? Go to football directly. Come in with your costumes and everything. I should have done it at 9 a.m., huh? 9 to 11? Well, when does the game end? It doesn't end that soon. What should we do? I actually have to teach also at the moment. What should we do? What's that? I do record it. How about you guys come in between, just bring a few pages and a pen. And then put the pen maybe somewhere in the corner and then come back on Monday and take it. I could take if there's a bunch of papers, I can take it on and bring it back to the practice exam. What? No, when I live stream, it doesn't record well. I tried it. This building doesn't record well. Let me see if I can change it to 9 a.m. But I mean, if you guys can come in and just leave right at 11, is that okay? How many of you guys are going to the game? I know the game is fun. Marching band, you absolutely cannot be here. So I will record it. That's one thing. Sorry about not realizing that. I thought I was doing it smart way. I didn't do it smart way. I apologize. But I'll try to see if I can open up. I'll talk to the back. Maybe not the entire thing would be recorded, but we record as much as we can. Yeah, that's kind of sad. Yeah, I really don't know what else I can do. Let me go ask and I'll let you know right afterward, like in 2 hours. But for now, it's 10 a.m. to 12:30 p.m. And then practice exam is on Sunday, 6 p.m. Exam is on Tuesday, 5:50 to 7:50 p.m. And covers what? 14.7, 14.8, 15.1 to 15.6, and 13.1, 13.2 likely. I mean, the points on that are going to be very light. Fair game? Okay. Again, apologies for, it's fun when you go to the game, they actually win. I don't want to not let you do that. And that's the, well, growing up and as a KU alumni, I tell you, it is much more fun when they win because I have all sort of experience. So, now let's try to do a few more. We're still in section 13.1. I was going to talk about this example very briefly. I want to show example 2. I want to show that R prime of t is orthogonal to R of t. Oh, wait a minute. What was R prime of t geometrically? Tell me what that is. Tangent, it's a tangent vector. What else? also a velocity vector. So I'm saying that tangent vector is orthogonal to position vector. This one is position vector, right? Always, if and only if magnitude of R of t is constant. So let's start with one way or another. I want to remind you, what is magnitude of R of t? Okay, better than that. What is magnitude of R of t to power 2? What's that? R of t dot R of t. Do you remember that? When I multiply a vector by itself, it's magnitude to power 2. Right? So now I'm saying magnitude of R of t is constant, right? So this is the same thing as magnitude of R of t to power 2 is constant, another constant, but still constant. This is the same thing as if I take the derivative of R of t dot, that's R of t, dot R of t is going to be equal to 500. 600? What would the derivative of R of t dot R of t be? 0, because this is R of t dot R of t. Right? So now, according to the rules that I just did, do you remember? I mean, it was yesterday, but 2 days ago. Derivative of R of t dot S of t is following what rule? Sorry, I didn't mean to go. It's following the product rule, right? What kind of product rule? Product rule that looks like this. R prime of t dot R of t plus R of t dot R prime of t is equal to 0. What is that? That's just 2 R prime of t dot R of t equal to 0. Wait, 2 is not necessary. R prime of t dot R of t is equal to 0. Oh, what does that mean? They are perpendicular. If the dot product of two things is 0, they are perpendicular. So this is nice. There's not enough that we do with physics just for planetary movement, basically. So this is something that may actually be helpful for physics and when you're studying the planetary movement. And this was what I showed you. When I say the position vector has a constant magnitude, it could be any curve on the surface of a sphere. Do you see that curve? It's not a circle. I mean, you can look at it in a circular way, sort of, but it's not a circle. But it's a curve on the surface of, and you can tell, do you see that black arrow outside this sphere? That black arrow is R prime. It's the vector, the tangent vector to the curve. Oh, I messed up something because the curve is not entire. There we go, now it's better. That's the shape of it. You can see that everywhere the position vector, which is inside, you can see the position vector inside is orthogonal to that, but it has to be on the surface of the sphere. The curve has to be on the surface of the sphere. Your turn. Questions? So how do I have a derivative being scalar valued and not vector valued? Is R prime, when R of t is a vector function, is R prime scalar or vector? What is R prime? We need a little bit more of a review, I think. Do you guys remember what, if R of t is a vector valued function, what is R prime? Let me write this down. Okay, guys, I think you guys need a little bit of review. Unrelated to the iClicker, I'm reviewing something for you. What is, let's say R prime of t is equal to t squared and t to the fifth and cosine of t. What is R prime of t? What's that? It would be derivative, component-wise derivative, right? Do you remember that from last thing I did? It might have been during the time you guys were going to take your quiz. Do you guys remember this? Okay. Derivative, this is a vector function. Derivative of vector function, is it vector or a scalar? That was an example. I'm just trying to review stuff. I think you forgot from last time. Now let's go back here. Derivative, is that a derivative of a vector function or a scalar function? Vector function. Vector function composed with a scalar, but output still going to be a vector. Is this a derivative of a vector function or a scalar function? Derivative of scalar function. Is this a derivative of vector function or a scalar function? Vector function. So which one is the scalar value for derivative? Okay. What? No, we're good? Which one? Where is alpha? Output. Yeah, the output has to be vector. Which one output is vector? Yeah, this one says the output is scalar valued. Which one is scalar valued? Yeah. Okay. 4, 3, 2, 1, 0. No, honestly, there are not that many people in class, I noticed. I heard. I don't want to hear, no. Oh, I heard there's somebody's meeting director of something or students. Yeah. Dean of Engineering? No. I told him. No. So you have to remember, Dean, you're seeing, let's say, if you're seeing something related to undergraduate, you're seeing Associate Dean of Undergraduate Study. No, he's the Dean of both. Okay, so that's, but he's stepping down. So I don't care if I tell you. So now the next step, well, I'm talking about smooth functions. Smooth vector functions. So do you guys remember when a function was not smooth in Calc 1? So, yeah, for absolute value, why is this not smooth? One more try. Think about tangent line. What is the tangent line this way? Goes this way. What about the slope of tangent line over there? There are two different tangent lines approaching that point. You're expecting two different tangent lines. So if a function is not smooth on a point that is defined, if vector function is not smooth, you're expecting that the tangent line is not defined. So the tangent vector is not defined. What is the tangent vector? R prime of t. Okay? So if R prime of t is equal to 0 vector, no direction is defined. Direction. The tangent direction, sorry about that off, is not defined. So the function, the vector function, vecfunc, is not smooth. So when R prime is that. Okay? So for example, the example that is given there is R of t equal to t to the 5 and t squared. Take the derivative. Where is this derivative? When is this tangent vector undefined? T equal to 0 gives me R prime of 0 is equal to 0, 0. R of t is not smooth at where? Now I want to give you the picture. The picture is right here. At t equal to 0, the tangent is not defined. And you have this picture that is coming this way. It's actually, the picture is not as well as I wanted, but it goes this way and then it goes, exits that way. Enters this way, exits that way. And so the tangent line is not defined. You guys good? In this course, when I talk about curves, I'm talking about smooth curves. Always. Sometimes I forget to say, remember that I'm always talking about smooth curves. Now, we talked about R prime of t, which was what? The velocity vector if t is time. And also the tangent vector. Sometimes I need trajectory. Do you guys know what trajectory is in physics? Trajectory is, I'm going on this windy road, and then if the road wasn't there, I would go in the trajectory of the tangent line. Right? If the road wasn't there, the friction wasn't there, I would go in the trajectory of the tangent line. So that's the trajectory. So how do I explain trajectory in mathematics? We go with the unit tangent vector. So unit tangent vector. It tells you about what direction you're going. Unit tangent vector is equal to, as you're expecting, the tangent vector divided by the magnitude of the tangent vector. Now, let me do the example very briefly. Something's up. I lost the page. Okay, for example, if R of t is t squared and t cubed minus 1, then r prime of t is going to be 2t and 3t squared. Oh, I copied wrong. This is not very smooth. I don't like it. One more try. And then what would the capital T or unit vector be? Magnitude of r prime, which is 1 plus. Would you guys excuse me? I want this to be exactly like your notes. R is t and t cubed minus t. R prime is 1 and 3t squared minus 1. And so the magnitude of r prime is this. And I have to divide r by that. So that would be the unit tangent vector. We're going to talk about this in chapter 16 a lot. That's another reason that I want you to remember that. Okay. A couple of items that are not as essential, but let's talk about this quickly and briefly. If you're taking antiderivative of a vector function, it's going to be component-wise antiderivative, right? But then if you're, for example, if you're computing it that way, it doesn't mean that your constant is going to be the same for all integrals. Let's try to do start one. Example 5. Given r prime this, and r is a position vector, and r prime is the velocity. How do I find r from if I have the velocity, how do I find r? If I have velocity, what do I do to find position? Integrate. So I'm going to integrate r prime of t first, which is integral t dt, integral cosine t dt, integral sine t dt. The first one is t squared divided by 2. The second one is sine of t. Third one is minus cosine of t. What am I forgetting? Plus c, all of them plus c or different? Plus c1, plus c2, plus c3. Now if I want to completely find the r of t, I have to plug in 0 in here, r of 0, what is r of 0 supposed to be? 0, 0, 0. Let's plug in 0 in there. 0 plus c1, 0 plus c2, negative 1 plus c3. What is c1? c2? c3? 1. So the answer to this question is going to be, I'm going to write it down, like that. Fair game? Questions? Are we up to this point? Can I start the next section? Okay. Which part? Which part? Molly, ask. No, you good? Okay. No. you're sitting in the middle of them. So, this section, arc length and speed. Do we remember arc length from Calc 2? What was the arc length formula? Approximately. So you had a y prime in here. What would you do with y prime? 2 power 2, square root of that, dx, a to b. Okay. Now, this was when y was a function of x. Now I have a vector function, and you still want to see the same song and dance. Let me put that over there. That was Calc 2. Okay, I want to make sure a couple of things. When I say arc length, let me see, I'm on this road, and I'm traveling, right? Arc length of this road from point A to point B is what my odometer shows. What's the one with the car? That's odometer. Yes, okay, I didn't mess it up. So my odometer shows how many steps, how many meters I traveled. And the road is curvy. This is different from displacement. So displacement would be, road is curvy, but I find a distance from the beginning and end point. But the arc length is the amount that I travel. So let's say arc length is the length of a curve between point A and B, points A and B. The displacement is different, and if position vector is r of t, is the vector function r of t, displacement looks like the magnitude of r of b minus r of a. I said that it's different, except if you're on straight line, the two of them are the same. They are the same only on straight line. Lines. So that's the story of that. Now I want to tell you a little bit, not this. Example 1. Do you guys know what kind of a shape this vector function is? Did you guys have any questions on that? No, we're good? Are you still there? Is this weekend just for the weekend to come and see me during the review? To come and see me during the review? Do you know what I'm doing? Whenever you sign something, there are little notes on the bottom, the agreement. Yeah, that was that agreement. So R of t, can you guys tell me, I mean, it tells you, but what is that? If R is constant. A circle of radius, R. And so what is the center of this circle? 0 and 0 and 0, actually. Because 3 dimension. It's actually in XY plane. and radius r. Now, when I talk about arc length between with this parametrization, arc length for length between A and B. What is T in here tells you? T talks about, let's say, the angle between the point and the x-axis. So basically, this would be A, and the big one would be B. Okay. So what would this angle be between the point A and B? B minus A. Okay. So what length of the entire circle did we cover? Think about fraction. This length over the entire circumference of circle. B minus A divided by 2 pi, right? That fraction of the circumference. So that's B minus A over 2 pi times, what's the circumference? 2 pi r, B minus A times r. So when I say arc length between t equal to A and t equal to B, that's what I mean, that length. Let me color it. That arc length. Fair game? We're good? Okay. So now let's see, do I have an eye? I have an eye clicker. Do an eye clicker so you can wake up. That's rude. Rude of me. My voice is so calming, it's like a lullaby. I think it's the lesson 1 of the course, right? Do you remember? Yeah? Hold on, I keep forgetting your name. Tell me again. Michael. Lucas.
When you subtract, like if you were to subtract the +1 minus the not +1, does that change the arrow from does it go from this way if you were to subtract this one?
So think about it this way. So r of ti plus 1 going that way, the negative r of ti minus 1 is opposite of ti, r of ti. And then if I add the negative r of ti plus r of ti plus 1, I want to start from the beginning point and end at the end point. If I do that, no, you have to do the other way around. The way you had it was correct.
So you want to subtract the bottom and the top?
No, the top from bottom. Because you want the entire thing to end up where you were at. You're ending up. You want both of them to end up at the same place. So when I'm subtracting, what am I expecting to do? Subtracting 2 vectors. This is A. This is B. If I go A minus B, A minus B, direction changes. Then I can add A and minus B. What do I get? I get this direction. That's A minus B. What's the answer here? Okay. Thank you so much. What? You guys? A lot of people got C. 4, 3, 2, 1, 0. So you guys agree with that, right? Now, why is there a fuss? So the fuss is about here. When I have a curve, like that, basically, what do we do in calculus? We make small pieces. What I'm trying to do with this curve is to approximate with little chord between, divide the entire curve into little arc lengths, and approximate each arc length with a chord. How do I compute each chord? Each chord is, I can use the position vector, just like we did right there. Yeah, the other way. This was so I can approximate each little arc length with a little chord, and little chord is approximated with that. So each arc length, small arc length, or infinitesimal arc length, delta Si, is going to be approximated by the length of each little chord. Let me go back to the picture, I'm sorry. By length of each little chord, delta Ri. And according to your iClicker, that is actually equal to the difference between R of Ti plus 1 minus R of Ti. Okay. Now, when I have the difference, using my knowledge from prior to this, I can actually use the derivative to approximate that. The difference at 2 points that are very close to each other is approximately delta T times magnitude of R prime of T. So the little small length is that. How do I find the entire length? Sum it up. Forgot I. And limit it to infinity, and that becomes an integral. Fair game? We're good? Okay. So what is arc length formula, my friends? That's the arc length formula. That I showed you how to get the arc length formula. The other way of showing arc length formula is this. That's a prime. T prime, prime, prime. F prime of t to power 2 plus g prime of t to power 2 plus h prime of t to power 2 dt, where r of t is equal to f of t, g of t, h of t. We're good? Example time? We're ready? Let's do the example. This is the nicer page. My handwriting can be bad. Honestly, this comes in handy a lot more than you think. I left a note on actual experience I had on the field with helixes. So this question is asking, a cylindrical tower is 30 feet high and has a radius of 10 feet. A spiral case wrapped around the tower 3 times from the base to the top of the tower. How long is the staircase? How long is this staircase? Is this staircase a curve? I want to find what am I finding? Arc length of the curve. So now let's see, what is the minimum z value for this? What's the maximum? 30. What is the radius? What is the radius? Radius is what? Between what and what? Radius is constant 10. Radius is constant 10. Now, you guys know this. How does x and y change if z is in this direction? It turns out that it doesn't matter if we go this way up or we go that way up. We get the same answer. But you need a little bit more knowledge on this to figure that out. So for now, assume we're going counterclockwise. So tell me, how do I parameterize x and y? X and y. One more thing to that. You're on the track, but one more thing. Don't forget that. 10 cosine of t. So I'm going round and round, but I'm going up. How's x and y changing? R cosine of t, R sine of t. So I get 10 cosine of t, 10 sine of t. Wait a minute. I start t at 0. When do I end with t? How many rounds am I going? 1 round, 2 pi. Second one, 6 pi. Now here is the problem. I want t to increase. I know it's a helix. I know z is a linear function of time, of t. I'm not time in this case. What I need to have is that z to be 0 when t is equal to 0, and z be equal to what when t equal to 6 pi? 30. Again, z is a linear function. How do I find that z? Find the slope. This 0, 0, and 6 pi and 30 are on that. So what's the slope of this? What's that? Oh, 6 pi because it says 6. I said 1 round, 2 pi. Second round, 4 pi. Third round, 6 pi, because I'm going 3 times. Right. So now so this is telling me that the point 0, 0 and 6 pi and 30 are on that line. What's the slope? 30 over 6 pi times t. Everybody followed that part? Are we good so far? So R of t is equal to 10 cosine t, 10 sine t, and what is 30 over 6 pi? 5 over pi times t. T between 0 and 6 pi. Check. If I plug in 6 pi, am I going to be on top? Or? They're practicing. Okay. Keeping you in review tomorrow is proven to be difficult. Okay, so now, that was not my end of it, right? I needed a vector function, so I can take the derivative of that, so I can find the length, arc length. Found the vector function, right? I parametrized. Now, this was the step 1. Vector function. Now, step 2, derivative. What is derivative of 5 over pi times t? Then find the magnitude of r prime of t. Oh, I took the derivative. Step 2 is derivative of the entire thing that I did was I was finding the vector function. The vector function that models that. Now I'm taking the derivative and finding the magnitude. 100 sine squared t plus 100 cosine squared t plus 25 divided by pi squared. And that is 100 plus 25 over pi squared. I put these two, I added as 100 times cosine squared t plus sine squared t. And then step 3, arc length is equal to integral. Where does t start? Where does it end? And what is magnitude of r prime? That. dt. Oh, this is very complicated, but it's a constant. Looks complicated, constant, it comes out. So what do I get? And that's the answer. You can clean it up a little bit, but it doesn't matter as much. You can take the pi in as pi squared. Get rid of the denominator. Approximately, this is 77.92 feet. How much time do I have? Do I have enough for this? Should we do this or not? Let's do it. No? Should we not do it? Okay, goodbye. See you tomorrow, though.
Since I'm like doing the gateway thing, when I come upstairs, will you guys speak on? If I'm doing it, if I'm not.
Oh, that's true. Because I'm going to be back here reviewing.
What?
I'm back here reviewing. So, yeah, I will not be here, but I'll be in this room if you come back.
Will Dr. Hutchins be up there?
I think she's reviewing too, but I'm not sure. I don't think there's any key down there because I opened the door, but I didn't leave the key down there.
Okay.
So I can go later and lock it.